It's a great pleasure to have so many guests here and faculty here today to hear what I'm sure is going to be an outstanding talk. I think there are very few scientists that can have achieved what our speaker today has achieved. To take a basic science discovery in multiple fields and take it forward and affect the lives of millions of people, including myself, who take statins. So I think that, you know, these scientific stories are actually quite fascinating. I never worked in this field of the LDL receptor, but two of my very close colleagues did, and I can remember the excitement that was building as the story unfolded. And it was like a, you know, I was going to you say a soap opera, but that's not right. I mean, it was like a serial where, you know, every 6 months or so there would be this brilliant paper that would come out, which would elucidate this pathway and explain the importance of cholesterol and the LDL receptor in humans. And it was a multifaceted approach: cell biology, biochemistry, human genetics, understanding metabolism, and then ultimately in the design of drugs and treatments for people to lower bad cholesterol in your blood. And Dr. Brown has achieved this over a 42-year career in Dallas. And he actually complained to me about the plane connections in Grand Rapids, but then I realized he's actually, you know, he lives in Dallas, which is the hub of the world's largest airline. So, of course, no matter what we do, Mike, we can never get as good as Dallas. I was amazed to see when I was reading his background that he started when he was 13 with an amateur radio operating license. And I myself remember how in Africa I was completely transfixed by radios and making crystal sets, and there were transistor radios just coming out at that time. And I think that's what got me in science, and may well have got him in science as well. He got a degree in chemistry from the University of Pennsylvania, and then got his medical degree 4 years later, also in Pennsylvania. And early on in his career, he had the good fortune to meet Dr. Joe Goldstein. And between the two of them, they worked to crack open this important problem. Dr. Brown is currently the director of the Johnson Center for Molecular Genetics at the University of Texas Southwestern Medical Center in Dallas, which, by the way, has the largest number of Nobel Prize winners in any American medical school. This is quite something. So it's my honor and my privilege to introduce you today to a man who chose science and whose groundbreaking work has really helped millions of people. And I think we're very, very grateful that you could be here. We're also very grateful for your work in setting up this institute. Dr. Brown was one of the chairs of the Scientific Advisory Board that David Van Andel set up, and Jay Van Andel as well, and recruited George Vanderwood here to get this institute up and running. So we owe him much more than just a thank you for the statins. We thank him for George and for the Van Andel Research Institute. So thank you for coming, Mike, and we're really thrilled to hear that your seminar. Thank you.
Thank you, Peter, for that very, very kind introduction, and welcome to the Van Andel Institute. I was involved with this institute before it was an institute, when it was only a vision in the eyes of a very few people. And I was approached by Luis Tomatis, for whom this auditorium is forever named. And I really don't think I'd ever heard of Grand Rapids. I'd never heard of Van Andel. I'd never heard of Amway. But he told me the story, and he's an inspirational figure and also a very persistent man. And so I became involved, and when I came here and met Jay Van Andel, David Van Andel, and the family, I realized they really were dedicated to building a great research institute. and overcoming the obstacle, which is putting a research institute in a city that had no other kind of research, and which at the time didn't even have an academic medical school. You know, I got caught up in the vision too, and I helped. And when we found George Vanderwood, I knew that God was looking down kindly on us. So now let me tell you the story of the work that Joe Goldstein and I have done in Dallas. Do you hear that echo? I don't know whether it's from the two microphones or what. Anyway, and we call this a century of cholesterol and coronaries. And it really is almost unbelievable. First of all, coronary artery occlusion, which causes heart attacks, is the most common cause of death in America and in the Western world in general. And yet we've only known about this disease for less than 100 years. It's really rather remarkable. And I'll tell you about the history of how this disease was recognized and how the link to cholesterol was made. And then I'll tell you about the work that Joe and I did to try to elucidate the mechanism. So these are the coronary arteries of a 43-year-old man who died of a heart attack. The coronary arteries supply blood to the heart muscle, and they've been opened here lengthwise, so you see these yellow deposits, which are atherosclerotic plaques. And we know that these plaques begin to form in the teenage years, but they gradually get more and more, bigger and bigger and more occlusive, and eventually a thrombus forms, a blood clot, that deprives the heart muscle of oxygen, and we have the crushing chest pain of a heart attack. Now the culprit, the thing that initiates these atherosclerotic plaques is a cholesterol-carrying protein that travels around in the bloodstream, and it's called low-density lipoprotein, or LDL. Now, there are several other lipoproteins that carry lipids in the bloodstream, but LDL is the most abundant cholesterol transport protein. And LDL is a spherical particle, about 22 nanometers. It's about the size of a small virus. And it has a core that is composed of cholesterol. So here is the structure of cholesterol. It's a 4-ring molecule with a hydrophobic side chain and only one polar part, which is this hydroxyl group. So cholesterol is a greasy, insoluble molecule. It doesn't dissolve in water. And it's actually used by the body to help make the plasma membrane that surrounds all the cells in the body. And so its insolubility in water is its chief characteristic. That's what allows it to stay in the lipid membrane that surrounds the cell. So every cell in the body needs cholesterol. But cholesterol can't be transported in solution like sugar or amino acids. It can't be transported in the blood that way because it doesn't dissolve in water. So nature solves this problem by taking the cholesterol molecule, attaching a long-chain fatty acid to this hydroxyl group to make a cholesterol ester, and then depositing them in the core of this cholesterol-carrying LDL. And each LDL particle contains 1,500 molecules of cholesterol in its esterified form. And then surrounding it, there's a polar coat composed of phospholipid, and a protein called ApoB, which directs the LDL particle to its sites of metabolism. Now, atherosclerosis begins when LDL particles from the plasma infiltrate into the wall of the blood vessel through the endothelial lining, generally at places where the lining is under stress because of turbulence or other factors. The LDL enters the wall, and there it becomes oxidized. And the lipids that are in LDL become altered by reaction with oxygen, which renders LDL in a form that is recognized by macrophages, scavenger cells, that secrete inflammatory cytokines. And the scavenger cells ingest the LDL, and they build up so much cholesterol that they turn into foam cells. When you look at them in the microscope, they have this foamy appearance because they're full of lipid droplets, fat droplets, which are composed of the cholesterol that's been ingested. So the combination of all of these events leads to the buildup of an atherosclerotic plaque, which in addition to cholesterol and macrophage also has calcium and fibrous tissue, which are created in response to these inflammatory cytokines. Now, the century of cholesterol began in 1910, when a pathologist in Germany extracted the lipids from human atherosclerotic plaques in the aorta. And he found that these plaques contained 25 times more cholesterol than the surrounding vessel tissue. And in fact, the disease had been named atherosclerosis from the Greek word atheros, which means gruel or porridge, because when these lesions were opened, this cheesy material leaked out, and Windaus showed that that cheesy material was cholesterol. And then 3 years later, Nikolai Anichkov, a young student in Russia, fed pure cholesterol to rabbits and produced the same atherosclerotic plaques that had been found in human aortas. And that was the first evidence that cholesterol could actually cause atherosclerotic plaques. But it wasn't until 1918 when the syndrome of a heart attack was first recognized in humans. Now, pathologists had known for many years that people would develop acute severe chest pain and die. And the disease had names. It was called apoplexy and other names. And sometimes at postmortem, the pathologist would find obstruction of the coronary arteries. And one of the theories was that the blood clot in the coronary arteries could produce this severe chest pain leading to death. But heart attacks were thought to be always fatal. There was no idea that one could have transient chest pain, have a heart attack, and actually recover from it, because it was thought that once a coronary artery was blocked, the heart would just stop beating. And so people who had chest pain but survived, it was credited to indigestion or other things. But in 1918, an American physician named James Herrick used the newly invented electrocardiogram machine to study patients who had come into the hospital with chest pain. And he found that there was an abnormality in the electrical tracing of the heart. The EKG measures the electrical activity of the heart, and Herrick identified an abnormal pattern in people who were complaining of chest pain, but remarkably, they didn't die, and most of them recovered, and their electrocardiogram again changed once they had recovered. So he presented a paper at a meeting, and he described for the first time the syndrome of a heart attack. And that was really the beginning of the modern specialty of cardiology in medicine. And it was really due to the technological advance of the electrocardiogram machine. Now, in 1938, just 20 years later, the first genetic evidence for heart disease was established. Carl Mueller, a physician in Norway, found families in which high blood cholesterol levels were being transmitted from one generation to another as an autosomal dominant trait. And he called the disease familial hypercholesterolemia, which just means familial high blood cholesterol. I abbreviate it as FH. And he described, not only did he describe the disease, but he also showed that nearly all of the patients who inherited this mutant gene and had a high cholesterol died of heart attacks, usually before the age of 60. So that was the first genetic link between high blood cholesterol and heart attacks. Now, all this interest in cholesterol stimulated some brilliant chemists to figure out how cholesterol was made. And two of the most important ones were Conrad Bloch and Fyodor Lunin, who shared the Nobel Prize for their discoveries. And they elucidated this really complex pathway because cholesterol is made, here's the 4-ring structure, 27 carbon atoms of cholesterol. But it starts out as 2 carbon precursor. And then it's acted upon by a whole series of enzymes that cause polymerization and eventually cyclization, and it leading to the production of cholesterol. There are about 30 enzymes required to make one cholesterol molecule. And an important step is catalyzed by this enzyme called HMG-CoA reductase, which catalyzes an early step in the polymerization reaction. I mention this because it becomes very important later in the talk. So, the cholesterol biosynthetic pathway had been recognized, and it was appreciated that all animals can make cholesterol, including humans. And that was the way it stood back in the early 1950s. In 1951, a cardiologist in Boston called Paul Dudley White collected 100 patients who came into the hospital under the age of 40 with a heart attack. And he was able to observe several risk factors, what he called risk factors, things that increased your risk for a heart attack. And remarkably, his clinical observations from 1951 are the risk factors that we recognize today. First of all, in these young people, he recognized that the male sex was very important. The vast number of his patients were men. Secondly, they tended to have very high cholesterol levels. They also tended to have cigarette smoking and high blood pressure, all of which we recognize now as predisposing factors. And this led to the concept that there are risk factors that increase the risk of having a heart attack. Now, all of these studies were done before LDL was discovered, and so we call that the era of cholesterol. But the second half of this century was the era of LDL, and it began in 1955 when John Goffman, who was a physician and a physicist in Berkeley, California, used another technological advance, the ultracentrifuge. And he took people who came in who had a heart attack, who had a history of a heart attack. He took their blood and he put it in the ultracentrifuge and spun it so that the force of gravity was 100,000 times, the centrifugal force was 100,000 times the force of gravity. And when you do that, the cholesterol in the plasma floats to the top because cholesterol is lighter than water. And it comes to the top in different fractions. And the first fraction to come up, he named low-density lipoprotein, or LDL. And he noticed that among people with a history of heart attacks, there was a marked increase in the amount of LDL in the plasma. This was the first identification of LDL as the lipoprotein causing this disease. He also noticed that the next fraction that spun to the top, he called high-density lipoprotein. And he noticed that the opposite was true for high-density lipoprotein. People who had low levels of HDL tended to have heart attacks. So he deduced correctly that a high LDL and a low HDL predisposed to heart attacks. Now that's basically was the way it stood until Joe and I entered the picture in 1973. And I'll tell you the story of how we discovered the receptor that removes LDL from plasma and how genetic defects in this receptor cause high blood cholesterol. But the next step was a crucial study in 1976 by a scientist working at the Sankyo Drug Company in Tokyo. His name is Akira Endo, and he discovered the first inhibitors of HMG-CoA reductase, the drugs that we now know as statins. And he discovered them by making extracts of molds, penicillin molds, and he found one mold that produced a chemical that would block this enzyme and therefore block cholesterol synthesis. And in 1981, Joe and I showed that when we gave LDL receptors to dogs, not only did it block cholesterol synthesis, but it also raised the LDL receptors in the dog liver. And that was the key to understanding, and that was the reason why the LDL level fell in plasma. And that was the key to understanding how a cholesterol synthesis inhibitor could lead to a selective reduction of a particular lipoprotein, LDL, in plasma. And I'll have a lot more to say about that in a minute. And then in 1987, now almost 30 years ago, the first statin was approved for human use. Not the Japanese statin, but an American statin developed by Merck, and it was called Mevacor. And then, at the time that Mevacor was approved, there was no evidence that it actually reduced heart attacks. The Merck showed that it lowered LDL, and the FDA accepted the idea that lowering LDL would lead to a reduction in heart attacks. But that wasn't proven until 1994, when Merck completed a landmark study called the 4S study, which it was conducted in Scandinavia, and it showed that not only did statins reduce heart attacks, but they actually prolonged life. So that's the century of cholesterol, from the first identification in 1910 until the approval of statins in 1987 and their therapeutic efficacy demonstrated in 94. Now let me tell you a little bit more about Joe Goldstein and me. Joe had been a medical student in Dallas, Texas, and I had been graduated from medical school at the University of Pennsylvania. And we met as residents at the Massachusetts General Hospital. I show this picture of the two of us as residents, not because we were handsome, although we were, but because we were young. And I think for the young scientists in this audience, you know, you see an old man like me get up on the stage and give all this history, and you picture some old man doing these experiments. Everything I'm telling you was done when we looked kind of like this. We were young. And we were trained in medicine. And we finished our residency at the Mass General, and then, by chance, both of us were accepted as fellows at the National Institutes of Health in Bethesda, Maryland. And there we saw a young girl with this disease. Now, from to be honest, this is not our patient. We weren't smart enough to have a camera, and we didn't take a picture of our patient. But this is another little girl with the same disease. So our little girl was 6 years old, and she was hospitalized at the National Institutes of Health because the LDL level in her plasma was 10 times above normal. Normally, in a 6-year-old child, the LDL level in plasma should be about 80, and hers was 800 milligrams per deciliter. In fact, she'd had her first heart attack when she was 3 years old. The LDL was so high in her plasma that it was infiltrating her arteries and occluding them, not at age 60 like we normally see, but at age 3. And we knew it was genetic because she had a brother who had the same condition and was also hospitalized at NIH. And not only that, but her parents, both of her parents, had moderately elevated cholesterol. The two parents had the disease that was described by Mueller in Norway, the autosomal dominant form of high blood cholesterol. Their cholesterol levels were 2- or 3-fold above normal. But when the children had inherited the mutant gene from both parents, now fortunately this is rare, it only happens in 1 in a million births, but because of this because the child inherited 2 copies of the mutant gene, she developed this massively high blood cholesterol. Now, you'll notice that this child has these bumps on her skin, which you can see in more detail here. How do these bumps, we call them xanthomas, how did they form? Well, if you fall down and bruise your knee, you get a black and blue mark. And what causes that? Well, the capillaries in the skin have ruptured because of the trauma, and blood, which is normally contained within the blood vessel, now leaks out through the capillary wall into the tissue itself. And so you get this swelling and the redness of a black and blue mark. This sends a signal to circulating monocytes, which are circulating in the bloodstream. They infiltrate into the tissue, and they convert into macrophages or scavenger cells. And these macrophages now scavenge up, eat up all the constituents of blood that have leaked out into the tissue. And basically everything that's in blood can be broken down to soluble molecules. Proteins are broken down to amino acids, complex carbohydrates are broken down, nucleic acids are broken down, but the one thing that can't be broken down is cholesterol. Our bodies don't have any enzymes that can break this ring structure of cholesterol. But the macrophages pick up the cholesterol, and then they leave the tissue, and your black and blue mark will eventually recede and disappear. When this young girl falls down and bruises her knee, and her plasma leaks out into the tissue, the monocytes come in, they scavenge everything up, but they consume so much cholesterol that they become swollen with cholesterol and they turn into foam cells, and they can't leave. So if you did a biopsy of this, the skin lesion, you would see exactly the same thing that you would see in her arteries. That is, these cholesterol-loaded foam cells that accumulate. It doesn't take much trauma. You notice this little girl comes from a society where they wear copper bracelets for health, and just the simple abrasion from the copper bracelet causes enough capillary leakage to produce these bumps in her skin. Well, Joe and I saw the little girl and her 8-year-old brother, and we were, absolutely confused, puzzled by what kind of defect could cause such a high level of cholesterol in the blood. And we thought, well, maybe it's the diet. So they were hospitalized permanently at NIH, so we could put them on a 0 cholesterol diet. So for 6 months, they ate nothing but vegetables and rice and fruits. And at the end of that time, their blood cholesterol hadn't gone down by 1 milligram. So we knew it had nothing to do with diet, We knew it was genetic because of the family history. And so Joe and I decided that when we could set up our own laboratories, we were going to work on this disease and see if we could figure out what was the underlying cause. Now, the problem was that Joe had been a medical student at UT Southwestern in Dallas, and he had promised our great professor that he would go back there to start a program in genetics when he finished his training. I was not exactly excited about moving to Dallas, Texas. I had grown up in the Northeast. It was only a few years after John F. Kennedy had been assassinated in Dallas. It was really not a popular place to go, especially since my other offer was San Francisco. And this is a lesson to all of you who've been attracted to Grand Rapids. Not that Grand Rapids is not a whole lot better than Dallas, except for the airport. But the fact is that convincing me, I wanted to go there because of I wanted to work with Joe, and it happened to be an incredible department of internal medicine that had been built up by our great professor. The problem was my wife. My wife was also from the Northeast. In fact, she graduated from the same high school that George Vanderwood graduated from in Queens, New York. And she really wanted to go to San Francisco. And she wasn't a hippie. I say that. This was in the hippie era, but she was not a hippie. But she did have a guitar. But I give her, every time I speak, I give her credit because she agreed to move with me to Dallas, Texas. I promised her it would be for 1 year. That was 43 years ago. We've raised 2 beautiful Texas daughters, but the fact is, spouses are very important. That's the bottom line. All right, so here we are in Dallas, Texas, and how are we going to solve this disease? Well, what we did was we took cells from some of these rare patients. Remember, this is only 1 in a million, but we were able to get some cells from patients like this and grow them in tissue culture, and also grow normal fibroblasts in tissue culture. And then we began, and the idea was that if she had a mutation that was somehow affecting her cholesterol metabolism, that we ought to be able to observe it in tissue culture, since the tissue culture cells would have the same genes that she did. You have to realize that this was very early. Tissue culture had not been used very much at that time for detection of genetic abnormalities. And here's what we found. And this slide, it's about 10 years of work on this slide. So what we found was that cells, when they were growing in tissue culture, required cholesterol. As I said, cholesterol is a required building block for the plasma membrane that surrounds the cell. And we found that cells have 2 sources of cholesterol. The cells can make cholesterol from this simple building block, and they have to go through this enzyme HMG-CoA reductase, and they can produce cholesterol. But what we also found that was new was that the cells had another source of cholesterol. They could use the cholesterol contained in LDL particles. And remember, cells are always grown in serum, and the serum contains LDL. And when cells are grown in the presence of LDL, they produce proteins on the surface of the cell which we called LDL receptors. And we found that the LDL receptors cluster in these indentations on the cell surface called coated pits. And the LDL binds to the receptor because the receptor recognizes this ApoB protein on LDL. And when the binding happens, this piece of membrane sinks into the cell, it pinches off and forms a vesicle or a little bubble inside the cell, and then eventually it delivers the LDL to lysosomes, which are digestive organelles within the cell. And there the cholesterol esters are hydrolyzed and the cholesterol is liberated so that it can enter the cytoplasm and it can be used by the cell to make plasma membranes. Now, it turns out when you grow cells in tissue culture, they preferentially use these LDL receptors to supply themselves with cholesterol. And they keep their own cholesterol synthesis suppressed or reduced. Now, if cholesterol builds up to levels beyond too high for the cell, then the cell will also turn off its LDL receptors. So there's a feedback control. The cells want just enough cholesterol to make their membranes, but not too much, or it will crystallize out in the cell and kill the cell. Now, what was the problem with the children's cells? Their problem was that they had mutations in the gene for the LDL receptor. They couldn't make LDL receptors, and they therefore could not take up or use the cholesterol from LDL. And the cells survived in tissue culture because now they upregulated the HMG-CoA reductase enzyme, and they made all the cholesterol they needed. So we were fortunate that there is this backup pathway that allows cells to increase their cholesterol synthesis when they don't have access to LDL. So the primary defect in these children were mutations in the gene that encodes the LDL receptor. Now, how does that cause a high LDL level in the body? Well, here, this summarizes the metabolism of LDL. LDL begins life in the liver, and it's secreted as a lipoprotein particle that's bigger than LDL and lighter, and it's called very low density lipoprotein, or VLDL. And the bulk of the lipid in VLDL is triglyceride, that is 3 fatty acids esterified to glycerol. And VLDL's job is to transport these triglycerides. So it circulates through capillaries, and an enzyme removes the triglycerides from LDL, and the fatty acids now are stored either in adipose tissue or they are burned in muscle. So this is the major energy storage form of the body. And when the triglycerides are removed from LDL, the particle shrinks down, but the only lipid left in it is the cholesterol ester, and the particle emerges from the capillary, and now it's mature LDL. And then LDL is rapidly cleared from the circulation by binding to LDL receptors. Most of the LDL receptors in the body are in the liver, and the liver clears the LDL from the body. Now, what happens in familial hypercholesterolemia? When the receptor gene is defective, people with this disease make VLDL normally. They remove the triglycerides, they generate LDL, but now the LDL can't enter the liver because of the receptor deficiency. As a result, the LDL remains in plasma where it builds up to these high levels and causes heart attacks. Well, we think we understand familial hypercholesterolemia very well, but then the question is, why do people with normal LDL receptor genes have LDL levels high enough to cause heart attacks? And remember, I said 1 out of every 3 people in our society die of heart attacks. But we all have normal LDL receptors. So why doesn't the LDL receptor keep our LDL level low enough so that we don't have to worry about heart attacks? Well, the reason is shown on this slide, as Time magazine said. And you know how old this is. This is not new. This is Walter Mondale and Gary Hart. Some of you may remember them. But it's the high-fat, high-cholesterol diets that we eat. Now, how do we know that? Well, we know it by a huge number of epidemiologic studies that show that in populations that where, for example, in China and Japan, where they eat very low-fat diets traditionally before the arrival of McDonald's and Kentucky Fried Chicken, the LDL level is extremely low. But the same Japanese people move to Los Angeles and their LDL level rises because they start eating our food, and their LDL level rises to the same levels we see in other Americans. So it is the high-fat diet, and this has led to a reevaluation of what a normal level of LDL is. So this is the population distribution of LDL cholesterol levels in people in North America and Europe. And for a 40-year-old man, the mean cholesterol level is about LDL level is about 120 milligrams. And when I went to medical school, we were taught that this was normal and that the only people that were abnormal were the ones in the upper 10 percentile of the population. After all, that's the way we define normal. I should point out that this shading indicates that we begin to see heart attacks when the LDL level is over 100 and they gradually increase as the LDL level increases. So we thought that the only abnormal people were people up here above 140 or 150 milligrams of LDL. But this is a very egocentric, ethnocentric way of viewing the world. If you look at and ask, what is the normal LDL level for a human being? What you get is this curve. It turns out that the median LDL level for a human being is not 120, but it's really about 80. And in fact, all of us are in the upper 10 percentile of the human species as a whole. Now, why is that? Well, it's because there are a lot of people in China and Japan, for one thing. But it's also because they have traditionally eaten these very low-fat diets that are low in cholesterol and low in saturated fats. Now, the fascinating thing is that if you look at newborn humans, you take blood from the umbilical cord of a newborn baby, and what is the LDL level in the umbilical cord of a newborn baby? Well, it's somewhere between 40 and 50 milligrams per deciliter. And it doesn't matter whether you're born in Shanghai or Grand Rapids or Tokyo, and it makes no difference what the mother has eaten. The fetal level of LDL is controlled at about 50 milligrams per deciliter. So when we're born, no matter where we're born, that's our LDL level. And if we stay in a society where we continue to eat a low-fat diet, it creeps up a little bit, but not that high. But if we eat the kinds of diets that we habitually consume, the LDL level goes much higher. Now, why should it be? Why should it be that a diet rich in cholesterol raises the LDL level? Remember the scheme I showed you about LDL. It begins life in the liver, and the intestine doesn't even appear on that scheme. Well, the reason is because of this feedback mechanism. Remember what we discovered, that when cholesterol builds up in a cell, whether it's a cultured cell or a liver cell, when it gets to a certain high level, it turns down the production of LDL receptors. So, here's what happens, as shown on the bottom. When we eat a single cholesterol-rich meal, nothing happens to our LDL. Many years ago, when it was still legal to do this, Joe Goldstein and I took some medical students, and we fed them a breakfast of literally, I'm serious, of a half a dozen eggs, about at least a half a pound of bacon, and a milkshake. And in the milkshake, we put some more eggs. And they ate this breakfast, and we had an indwelling catheter in their vein, and every hour we took a blood sample and measured the cholesterol level. Now you'd think with this enormous high cholesterol meal, their blood cholesterol would shoot up through the roof. Turns out that over the next 24 hours, nothing happened. They were perfectly normal, the cholesterol level. And the reason is because when we eat cholesterol and it gets into our intestines, it gets incorporated into a different kind of lipoprotein particle called a chylomicron. And that particle delivers the cholesterol directly to the liver. It doesn't hang around in the bloodstream. When you eat cholesterol, it basically goes right to your liver, so it doesn't raise your blood cholesterol level. But over time, when we keep habitually eating more and more cholesterol, the liver begins to fill up with cholesterol. And when the liver cells accumulate too much cholesterol, the feedback system comes into play, and the liver turns down its production of LDL receptors. So we still make VLDL, we metabolize it, we generate LDL, but now the LDL is blocked from getting into the liver. Now, it's not 100% reduction, or we'd all look like FH homozygote children. It's probably no more than 10 or 20% reduction in our LDL receptors, but it's enough to raise our LDL levels from the level of 80 that we see on low-fat diets up to the level of 120 that we see on high-fat diets. I'm going to skip this slide on the way of time. So we have these low LDL receptors in our liver, and the question is there any way that we can fool this regulatory system and increase LDL receptors in the liver? And this is where Akira Endo and his discovery in Japan comes in. Endo, as I mentioned, was screening penicillin molds, and he found this molecule, which was called compactin, in which these two, R1 and R2, are both hydrogen atoms. And he was assaying for inhibitors of the HMG-CoA reductase enzyme. So here's the HMG-CoA substrate. This is the product, mevalonic acid. You notice that this chemical from this mold has the same side chain. This is a 5-membered lactone ring that's exactly the same as mevalonic acid. And indeed, this is a transition state inhibitor. It's a very high affinity inhibitor of the HMG-CoA reductase reaction. It's highly specific, and it blocks just this enzyme, and it was the first statin. Now, when Endo made his discovery and published it, we were immediately excited because we thought that this might give an opportunity to raise LDL receptors. And the theory was that even though this cholesterol has accumulated in cells and has turned down LDL receptors, the inhibition of cholesterol synthesis by cholesterol has not been complete. So there's still the biosynthesized cholesterol is still making a contribution to the total cell's cholesterol. And so we reasoned that if we could give a reductase inhibitor to the cells, it would lower this limb of the cholesterol axis, and as a result, the cholesterol level within the cell would fall, and that would lead to a removal of this inhibition, and so you'd get more LDL receptors. And we tested that theory. First, we showed that it works in tissue culture cells, and then we tested it and showed that it worked in dogs, and then other people did clinical trials in humans. And what happened was, if you take normal subjects, these were people with an LDL of about 120, and when they were treated with one of these HMG-CoA reductase inhibitors, their LDL level fell by about 50%. But you notice that in these FH homozygotes who start out with this very high LDL, there's almost no response. The reason there's no response is because these young people with this high cholesterol, they don't have an LDL receptor gene to turn on. So even though you block their cholesterol synthesis, they can't lower their LDL because the LDL receptors can't go up. And these are FH heterozygotes. They have one copy of the normal gene and one of the mutant gene, and they show a diminished response to the statin drugs. So for the first time, we had a simple oral medicine that could reduce the LDL level by turning on LDL receptors. And this led to clinical trials to see whether this reduction in LDL would improve heart attacks. And these are the results of, it's a meta-analysis of 170,000 people who participated in 26 randomized 5-year trials, where half of them were given placebo. These are people who had a known coronary artery disease, and so they were at high risk for a heart attack, and they were given either a statin drug or a placebo. And what the conclusion is that the decrease in heart attacks is directly proportional to the decrease in LDL cholesterol, and there's no lower threshold. That is, the lower the LDL, the fewer heart attacks. And in these randomized studies, there were no significant toxicities or increase in deaths. And this meta-analysis was performed by 2 fantastic epidemiologists at Oxford University in England. So now, it is true that in general use, some people cannot tolerate statins because they develop muscle pains or cramping or stiffness in their muscles. Generally, there's no objective sign of any muscle damage, but people can't tolerate them because they cause this pain. I note that in these 170,000 participants, when they didn't know whether they were getting a placebo sugar pill or a statin, there was no increase in muscle complaints in the people on statins. 4% of the people on a statin complained of muscle pain, and 4% of the people on placebo complained of muscle pain. But in general use, there are people who cannot tolerate statins because of muscle pain. This slide summarizes 5 studies in which statins were used in a 5-year trial. Again, these are patients who have coronary heart disease. They've either already had a heart attack or they have demonstrated blockage by angiography. And each time, people were either given a placebo, shown in the circles, or they were given one of the statin drugs, shown in these triangles. And what you can see is that in each case, the LDL level was lowered by the statin, as you see by the horizontal movement, and so were the coronary events. And it's almost a linear response. Now, there are a couple of interesting things about this slide. One is the original study, the 4S study done by Merck in Scandinavia. The amazing thing about this trial is they took people who had an LDL cholesterol level of 190, and half of them were given a sugar pill placebo for 5 years. Now, if you did that in the United States or in Scandinavia right now, I'm sure you'd go to jail, and you might actually be tried for murder, because anybody with an LDL level that high who has coronary disease can't be denied a statin. But back in the late 1980s, when this study was done, it was considered perfectly permissible to give a placebo to somebody with an LDL of 190. Now, you notice in the more recent studies, all the placebo, they weed out the people with 190s, and so all the placebo groups had lower starting LDL levels, where it was considered permissible to give them a placebo. This is a very interesting study. In this study, people were given 10 milligrams of atorvastatin, and they selected the ones who got their LDL down to 100, and then half of the group was increased from 10 milligrams to 80 milligrams, and the other half was left at 10 milligrams, so their LDL stayed at 100, whereas the people that were bumped up, their LDL fell to 70. And what you can see here is there was a further reduction in heart attacks. Well, to me, one of the striking things about this graph is look at how far we've come. In the 4S study, 25% of the patients had a repeated event over that 5 years, 1 out of 4. And now we're down to 5%, 1 out of 20. So that's progress, I think. And because of this gradually accumulating data, there's an NIH had a committee that recommends the target for LDL. And when they first met in 1987, they said that if you're at high risk, you should try to get your LDL down to 130. And the last time they met, they said if you're at high risk, you should try to get your LDL down to 70. Okay, let me just finish by talking about the most recent findings. The question now is not only how low, no longer how low, but how long should we treat people? And the reason came from a study of this protein, which has a crazy name, but it's called PCSK9. PCSK9. PCSK9 is a protein that's secreted by the liver and other organs. It circulates in plasma. It comes back to the liver, it binds to LDL receptors, and it destroys LDL receptors. We have no idea why the body makes this protein, why it should want to keep its LDL receptors partially reduced, but it's true in humans and all other vertebrate species that this PCSK9 protein is made. So all of our LDL receptors are not active because this PCSK9 protein keeps destroying them. But some people have a mutation in PCSK9 so that their PCSK9 doesn't destroy their LDL receptors. They have higher LDL receptors and they have low LDL. And these people, as I will show you, have a marked reduction in heart attacks. And this has led to the development, to companies developing anti-PCSK9 monoclonal antibodies for lowering LDL. And the breakthrough here was also done in Dallas by, not by me and Joe, but by our colleagues Helen Hobbs and Jonathan Cohen. And they took the population of Dallas and they took all the people with low LDL levels and they sequenced a bunch of genes to see if they could find mutations that led to low LDL. And what they found was mutations in the PCSK9 gene. So among Caucasians, 1 in 30, that's about 3% of Caucasians, have a mutation that substitutes one amino acid for another, and there's a partial loss of function of PCSK9. And because of this partial loss of PCSK9, their LDL is 15% lower than the control group. But remarkably, they have a 45% reduction in heart attacks compared to controls without this mutation. But even more striking is the situation in African Americans and in African Africans. 1 out of 50 African Americans has a severe loss of function mutation in one copy of their PCSK9 gene. And as a result of this severe loss of function, their LDL level is reduced by 30%. But the most remarkable thing is that their heart attack rate up to age 65 is reduced by 90%. 90% reduction in heart attacks with a 30% reduction in LDL. This slide compares the effectiveness of the PCSK9 mutation versus what we get with a statin. So if your LDL cholesterol is lowered by 15%, and that 15% lowering is caused by a PCSK9 mutation, your heart attack rate is reduced by 45%. But if it's reduced by a statin, your heart attack rate is only reduced by 15%. So the PCSK9 mutation is actually threefold more effective than the statin. And it's even more significant when you look at these severe PCSK9 mutations that lower LDL by 30%. They reduce heart attacks by 90%, whereas the same lowering with the statin only reduces heart attacks by 30%. So why should the PCSK9 mutation be so much more effective than a statin? And we obviously don't know the answer, but my and Joe Goldstein's idea is the difference is that people with a PCSK9 mutation have had their low LDL levels all their life. We know that atherosclerosis starts by age 20. And these people have had low LDL levels their whole life, and so likely they have never actually formed atherosclerotic plaques. On the other hand, the people who were treated with statins in these studies, all of them already had coronary heart disease. They already had these big buildups of cholesterol. So lowering the LDL at that stage is much less effective than it is lowering the LDL earlier. So this kind of observation has led at least 3 or maybe 5 drug companies to design monoclonal antibodies that can be injected and will neutralize PCSK9 so that the LDL receptors increase. And this is the results from one of those trials published in the New England Journal. And what you can see is they injected different doses of their anti-PCSK9 antibody, and what you can see, they got this dramatic reduction in LDL. At the highest dose, there was a 60% reduction in LDL that persisted for about 3 weeks. So these antibodies are being developed now. There have been many, many studies showing that you get this consistent lowering of LDL by blocking PCSK9. They have to be injected about every 2 weeks in order to maintain the LDL low throughout this time, although one company is trying to develop one that can be injected once a month. And, so we think, and I should add that this is the result you get when you inject the anti-PCSK9 antibody alone. But if you give a person a statin and the anti-PCSK9, the LDL level can fall by 80 or 90%. So we will have, I think, and I point out these drugs have not been shown to reduce heart attacks. They've just been shown to reduce LDL. And they produce a result that's consistent with the genetic data showing that people with mutations have fewer heart attacks. And so then it may be a few years before these drugs, the monoclonal antibodies, are approved, if they are approved. So, so let me just finish by summarizing the evidence. There are 4 lines of evidence that summarize the century of cholesterol and coronaries. 4 lines of evidence that establish the link between cholesterol and specifically between LDL and coronaries. First is the experimental. Simply feeding cholesterol to an animal sufficient to raise their LDL level will cause atherosclerosis in any animal species that's ever been studied. Secondly, there's the genetic evidence. People with mutations that raise LDL have more heart attacks. People with mutations that lower LDL have fewer heart attacks. Then there's the epidemiologic evidence. Populations that have high LDLs have high heart attacks. Populations that have low LDLs have low heart attacks. And finally, there's the therapeutic observation. Lowering LDL with statins lowers LDL and reduces heart attacks. Now, any one of these, one could think of something that might prevent the conclusion that LDL is responsible for heart attacks. Every one of them. But when you add all 4 of them up together, I think it's pretty incontrovertible. And I think we have the ability to abolish heart attacks by lowering LDL. The problem is who to treat. Because you take 2 people with an LDL of 120, and one of them will have a heart attack and the other won't. And how do we decide in advance which one is the one destined for a heart attack? Well, right now we use ancillary factors. If one of them smokes cigarettes, they should be treated. If they have diabetes, that certainly increases the probability of a heart attack. If they have hypertension, that increases. So we use things like that, the risk factors, and I should point out that in the people with the PCSK9 mutation, especially the African Americans, with a 90% reduction in heart attacks, despite the fact that hypertension is very common in that population. Cigarette smoking is also common, as is obesity and diabetes. So the fact is that despite those other risk factors, we know that if you lower LDL enough, you can reduce heart attacks. So when somebody has an LDL of 120, we look for those other risk factors to help us decide whether that person deserves treatment, prophylactic, preventive treatment. And we also use family history. If somebody's father and 2 brothers died at age 50 of heart attack, and this guy's 49 and a half, I think you'd probably start a statin drug. So there's family history and these risk factors, but they're not precise enough. And we need, desperately, we need some way of picking up the earliest signs of atherosclerotic plaques before they become big and threatening, so that we can screen people and identify which of them needs to have aggressive LDL-lowering therapy. And if we could decide who needs the therapy, I think we could abolish this disease which has killed so many people over the last century. Once again, let me thank you very much for inviting me. It's been a great privilege to be associated with this emerging institute, and congratulations to all of you for being here. Thank you. I'll take a couple of questions.
Thank you very much, Mike. Absolutely amazing presentation. Dr. Brown needs to get to the airport pretty soon. We have time for just 2 questions. If anybody would like to go to the microphone and ask a question. Jana, you asked your question earlier on this morning.
So, Dr. Brown,
Yes.
where were you and what were you doing the moment you learned you were a Nobel Prize winner, and what did you think?
I was, Joe Goldstein and I had been invited to MIT for a big symposium, and they asked us to give the introductory plenary lectures, which was on a Sunday evening. We gave those lectures. We went to a party at MIT. We went back to our hotel, and at about 6 o'clock in the morning, the phone rings in my room. I pick it up, and it's a woman, and she says, "Dr. Brown, how do you feel?" And I said, "What are you talking about? You just woke me up. How do you feel?" I said, "Why are you asking me this?" She said, "You mean you don't know?" And I said, "No." She said, "Well, I'm calling from the Reuters news service in Washington." And I said, "Well, what are you calling me about?" She said, "Wow, you don't know." And she was really flustered. "I'm the first person to tell you." "What?" It just came over the wire. You and your colleague are to share the Nobel Prize. So how do you feel? So I said, "Well, I'm totally shocked." Okay. So I hang up the phone. Immediately it starts ringing again. It's another reporter. "What's your reaction to the Nobel Prize?" "Well, I'm surprised and shocked." Hang it up. And this just went on and on because they were coming in. The calls were coming into this switchboard, and they were just, in those days they had operators and they were backing them all up. And I was trying to hang up the phone and pick it up for a dial tone so I could call my wife and tell her. And then I realized that she had to know, because the only way these reporters found us was they must have called my house, and she said, "Oh no, he's up in Boston, call this hotel." So then I wanted to, of course, share the news with Joe, and his room was across the hall from mine, and I wasn't very well dressed, and I didn't really want to run across the hall. But then I heard his phone ringing, so I knew he was going through the same thing. The interesting thing is that one of the other guests at this symposium had the next room down from me, and he told us later that he heard our phones ringing early that morning and decided, my God, it must be their lab people calling them with results, and they must really be dedicated to their lab. Anyway, that's how I found out.
Question up here.
Hello, Dr. Brown.
Yes.
So my question is regarding your hypothesis between the difference in efficiencies of the statins and the PCSK9 mutations. Since you mentioned that the people with the PCSK9 mutations probably did not have atherosclerotic plaques to begin with, that's why the efficiencies were higher.
Right.
So in patients where the monoclonal antibody was given, those people probably had those. So did that shed more light to the hypothesis?
That's a very good question, an excellent question. And it's going to be complicated. So right now, the 5-year trials have been started, okay? So they're going to count heart attacks in people who are treated with anti-PCSK9 versus a statin. So we'll know whether the acute treatment works, whether acutely lowering PCSK9 after the plaques have formed will work. And it's conceivable, or maybe very likely, that PCSK9, even in that setting, will be more effective than the statin, because the anti-PCSK9 is getting their LDLs lower than the statin. So some people will argue, if it comes out that it's better to take anti-PCSK9, they'll argue that that the whole thing, the only reason for the more effectiveness of PCSK9 is the fact that they get lower LDLs. But the point is, in that setting, we're lowering LDLs by 60 or 70%. In the mutation setting, it's only a 30% lowering of LDL that's causing this dramatic reduction. So we don't know the answer. Right now, the statin studies, when they do angiography or even better, ultrasound to measure the size of the atherosclerotic plaques, the statin studies have shown that there's really no decrease in the size of the plaques when you give statins. The reason they don't have heart attacks is because somehow the plaques become more stable, less inflamed when there's no more LDL coming in. But it's conceivable that if we could lower LDL enough, the plaques will actually regress. And that's going to be the other outcome that's going to be looked for in the PCSK9 studies. Okay, thank you very much.